Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be looking at the third law of thermodynamics. This video is going to be probably shorter than most for the simple reason that I'm making it more for the sake of completion than because I think that you're going to need an especially detailed understanding of the third law of thermodynamics. Most of the introductory level courses in physics basically skim this topic or mention that it exists and then move on. In the physics discipline, we often encounter it in a bit more depth when taking the usually junior-ish level thermodynamics course. And I'm not going to really break with that tradition much here. So what is the third law of thermodynamics? Well, at this point, you have encountered the first and second and zeroth laws, which I'm not going to summarize here. You can go watch the videos on those. Basically, you have a law that helps define temperature. You have a law which is thermodynamic conservation of energy. That's the first law. And you have a law that governs energy efficiency that has several different versions of how it is stated that are all equivalent to each other. And that's the second law. You also maybe have studied Carnot engines a little bit, and Carnot efficiency and so on. And the third law kind of ties everything together from an introductory standpoint. There's sort of two broad ways of looking at it. One is just strictly as a temperature law. So, third law of thermodynamics, let us say we can give it a temperature statement and an entropy statement. So temperature statement basically is that if you have a system or object or what have you, which is at a finite temperature, then you cannot in a finite number of steps lower that temperature to the absolute zero temperature. Essentially, what this means is that you can approach the absolute zero temperature, but you cannot actually achieve it. And experimentally, this has been kind of borne out. We have a value that is the absolute zero temperature on the Kelvin scale, and we have approached it. We can get within, maybe to a temperature of 10 to the minus 7 or so in Kelvin, but we can't lower all the way to 0 Kelvin. So you'll recall from our previous videos how is the absolute zero temperature established, and experimentally you can do that by looking at a pressure versus temperature curve for an ideal gas and see where the pressure hits actually zero. Should be where the temperature also hits zero. That's kind of like how we first found a value for absolute zero. Now there's more to it, of course. Kelvin, for example, used the temperature scale to define temperature in terms of the hot and cold reservoir of an ideal Carnot engine. Another way of looking at the absolute zero temperature is that it's the temperature at which the system is at its lowest combined kinetic and potential energy. Now that doesn't necessarily mean that the kinetic energy is actually zero there. Quantum mechanically, you can't guarantee that you have stuff at zero kinetic energy, just because of the uncertainty principle. But for our purposes, any of these different ways of measuring this this absolute zero temperature, you have a temperature that you cannot actually reach. Now there's a second way of considering the third law of thermodynamics, which is that the entropy of the system approaches a constant value that's independent of external constraints like pressure or that kind of thing. Some constant value that the entropy approaches, and it approaches that value when the temperature approaches zero. So another way in the entropic statement might be that you cannot force the entropy of the system down to its minimum value in a finite number of steps. Noting that this minimum value is the value that's being approached by the entropy as temperature approaches zero. Now, worth noting here is that the entropy of the system may or may not actually approach zero as temperature approaches zero. It depends upon your system. The entropy of your system is given by basically the sum of what's called the residual entropy and the Boltzmann's constant times the natural log of the number of microstates, where this residual entropy S naught is the entropy approached as temperature approaches zero. So we could also say as T approaches zero, S approaches S naught, the residual entropy. And that residual entropy is actually zero or as close to it as we can determine for certain systems, like basically an ideal crystal would have S naught equals zero. But for other substances like glass, let's say, this will be a non-zero residual entropy. And then recall that this right here is number of accessible states or microstates for the system. And generally speaking, as T approaches zero, this number of states accessible approaches 1 for each thing, and the natural log of 1 is 0. So you could say something like this approaches 1 as T approaches 0, and of course the natural log of 1 is 0. So that is the statement of that portion of it. Okay, what about this temperature statement, the original statement that I wrote up here? Why is it that we cannot reach absolute zero with a finite number of steps? Well, in some sense, consider a simple system consisting of maybe like a gas or something like that. So you can cool the gas to very cold, like maybe 4 Kelvin, just by using liquid helium to remove heat from it. All right, so that drops us to 4 Kelvin. But now you have to cool it further. And how are you going to do that? Well, for a gas, maybe you can allow the gas to expand, but as long as the volume remains finite, according to the ideal gas law, the temperature will also be finite. According to the ideal gas law, pressure times volume should be equal to the number of particles times some constant times the temperature. Okay, and so that means that the temperature should look like PV over some set of constants, and therefore my final temperature over my initial temperature will look like my final pressure and volume divided by these constants over my initial pressure and volume, again divided by the same set of constants. So we can cancel out the constants. This means that my final temperature must be equal if I want this to be 0, this must be equal to the final pressure times the final volume divided by the initial pressure times the initial volume times the initial temperature. Well, in order to make this number right here 0, I basically have to make one of these two numbers 0. I know that if I make the gas contract, that doesn't actually tend to cool the gas, so I really am needing to expand the gas to make the pressure hit 0. And how much do I have to expand this gas in order for this pressure to finally be 0? Well, I would have to expand it an infinite amount. So for PF equals 0, need volume final to approach infinity. And that obviously cannot actually happen. I can't make my gas actually hit an infinite size. And so this is sort of like the ideal gas law version of why we can't get to 0 temperature. In a finite number of steps, we would need to have an infinite number of steps to make the gas expand out to infinity. Now, there's other ways, of course, of actually trying to cool something than just putting in a gas state and expanding. But if you have some solid system, how might you cool that? Well, basically you need to cool it by removing any heat from it by running something even colder over it. Well, eventually you get it to where it's not, maybe it's not very warm at all, maybe it's very, very cold, but you don't have anything colder to remove whatever remaining heat is left. So what can you do? Well, you can try to isolate it in vacuum and let it radiate the heat very slowly. But remember that any time that it radiates heat outward, there's also the possibility of its absorbing radiation from the outside in and heating. So that process ends up not working so well. Essentially, there's no way to actually isolate the thing to where it can only radiate and never absorb. If you put it inside of like a box or something like that, then the box itself can re-radiate back to the object and heat the object. All right, so that's a no-go. With a gas, you can try laser cooling. That's how we actually get stuff down to these very, very cold temperatures. The idea being that you have, let's say, a molecule which happens to be moving this way, and maybe it's a free molecule, and then it absorbs a photon traveling from the opposite direction, slows it down. Well, that's possible as long as it doesn't re-emit the photon, and of course they can spontaneously re-emit photons in any arbitrary direction and then start moving again. Not to mention that eventually you end up with a gas in which, yeah, most of the particles have slowed to the slowest that you're going to be able to get them, but there may be others that are still moving very quickly, and further trying to irradiate your sample will tend to make the slow particles start speeding up more often than making the fast ones slow down again. So you run into a kind of barrier there as well. So the point being, you can't get all the way to the absolute 0 temperature. And that's all for today's video. Hopefully you learned something.